science like there's no tomorrow.
Hello, welcome everyone to the fourth lecture of the financial engineering course with special focus on interest rates and XVA. Today we will discuss further the concept of short rate models, and we will relate short rate dynamics to dynamics of a yield curve. I will also discuss the concept of the extension of a single factor whole-wide model to multi-factor whole-wide model, and we perform a number of simulations. Let's take a look into details. First, I will show you how to find an exact solution for the whole-wide model. Finding exact solution for the whole-wide model is slightly different than we have seen before for geometric Brownian motion or arithmetic Brownian motion. The reason for that is that the whole-wide model is mean reverting. So it is not just diffusive, how we have seen before. Here we have to do a little trick to get in an elegant way to find a solution for the process. Second point, I will discuss the affinity of the whole-wide model. So in the course of computational finance, we have already shown what are the conditions for the process, such that the model belongs to the class of affine jump diffusion processes. And once those conditions are met, we are able to find the characteristic function. Of course, whole-wide model, it belongs to the class of jump diffusion processes, of affine jump diffusion processes, for which we are able to find the characteristic function. In this point, I will concentrate on the connecting characteristic function or discounted characteristic function to zero coupon bonds. We will see that once we know the characteristic function, or we know the discounted characteristic function, we have essentially, at the same moment, we have zero coupon bond, which is in terms of that characteristic function. So this is very important and a very handy observation. Then we will go into a brief introduction to yield curves. We will have a whole dedicated the 2 lectures from now, where I will spend 1.5 hours on discussing different aspects of yield curves. We will also build yield curve ourselves in Python. We will use different market instruments to build this curve. So there will be much more depth in 2 lectures from now. Today, I will show you enough information so that we can link the yield curve and also short rate models. And that will be particularly important once we talk about extensions of a single factor whole-wide model to multi-factor model. So what we will be doing here, I'll be discussing different shapes of yield curve. We'll be also looking, there is some simulation from the market data, where we will be looking at the dynamics of a yield curve depending on the short rate. And that experiment, so the linking whole-wide model to yield implied from the short rate, I will connect that to the real market experiment. So you will see there is a nice video where we look at the real market data, so the Fed funds, and we will have a nice experiment where we compare Fed fund rate to yield curve observed in the market, and we will try to replicate that using our simulation of a whole-wide or whole-wide 2-factor model. We will try to improve, let's say, single factor model with multi-factor to add dynamics of the yield curve. And this will be also discussed here. So this will be the limitations of the single factor model. I will show you what are the big problems with the single factor model and how to solve them. And that will be the solution, of course, will be 2-factor model for the problems I will discuss here. I will give you details how to construct 2-factor model and how to simulate that. We'll also go into Python experiment where we'll be comparing 2 models in terms of the dynamics of a yield curve. And I will end this lecture with a summary and 2 exercises as the homework. I hope you enjoy it. We have a good 1.5 hours ahead, so have a good time. Although whole-Lie and whole-wide models are normally distributed, this means that at every time step t, random variables are following normal distribution, the properties of those 2 processes are significantly different. So the whole-Lie model is not a mean reverting process. This is just an arithmetic Brownian motion. So it's a normally distributed process with some drift, which is diffusing in time. On the other hand, the whole-wide model has mean reverting paths. And that makes it also slightly more difficult to find analytical expression for the solution for the process RT. Here I have illustrated a 3D plot where we show the generation of the path. So this is typically when you see paths, you see these two axes. So we see time t, and here the value of the path for process RT. So those are mean reverting paths. So normally I plot those paths in this sense. So we have here time. Here we have interest rate. Typically in the lecture, I'm always generating paths like this. So now this axis is basically here. So here we have paths, and then as time goes on, we have more and more paths, and this is some way diffusive. And then if we look at each slice, we look at the distribution of those paths, then we have a normal distribution. You can see here the right-hand side, I have indicated with the red tail, you can see. This is the probability in the part of a density which corresponds to the negative interest rates, which in both in fully and full white are possible. On the other side, so this is the full white model. If you have a fully model, then those paths basically will be just going like this, and there will be not mean reverting. In a full white model, we have mean reversion around the mean. Maybe I made this picture slightly more blurry, but I think you understand the concept here. Of course, we can also have a CIR model, and this kind of distributions also you can present in this way. This is a very illustrative figure because it shows you also that paths always, if you talk about distribution, you always need to look at the slice. Yeah, so we choose parameter time t, and then we look at this direction. Then we look at these distributions. As you remember from the first lecture, from the second lecture of this course, when we talk about stochastic processes, stochastic process is a random variable parameterized in time. So if we keep time fixed, then we have only random variable, and then we could look at these distributions. And you can also see here, there's some, in time, this distribution is wider than in the initially. Of course, if we are close to zero, then this distribution is very, very much narrow. Let's try now to derive the distribution, the solution for the Hull-White model. And the derivations for the Hull-White, it's one very elegant way to do that. If we define a process yt, which will be e minus e to lambda t rt. So this is just a small transformation. This element here, it kind of, you can think of extracting away the mean reverting part from the Hull-White model. This is also related to the HJM volatility structure, where we had this sigma times e to power lambda t minus lambda t. And this is the same kind of scaling we are doing here. Of course, you can also derive this solution in a different way, but I particularly find this kind of elegant way to do that. And if we have this definition of a process, so you can see that it's always possible to define process yt, because if I would just divide both sides by e to power lambda t, then I'm going back to rt. So this is just a convenience choice. How we scale, we can do whatever we want, as long as this scaling is continuous and well behaving, then this doesn't really matter what we choose here. This particular choice, what will be happening, it will be very handy to do. So if we have this process and we apply Ito's lemma to it, then we end up with this dynamics. So with a dy equal to lambda yt dt, and then we have a exponent lambda t drt. So of course, because we know the distribution, we know the drt, so this is Hull-White, we can substitute the dynamics for the Hull-White to this expression. And this is what we get. So we have, again, the drift is the same as here. Here we have a scaling, and then we substitute the dynamics for the process RT. If we collect the terms, so we can actually see here that because we did this scaling here, if we look here, so we have E yt, then we have times minus rt, and on the other hand, we also see that we have a yt, which is defined in this way. So this process, we can substitute this for yt, then we see that it will be lambda e lambda t rt, which will be the same, which will be canceling out with this term. So we will have e lambda t times lambda, and then with a minus rt. So this is nicely cancels out. And this is actually the whole, let's say, elegant idea here, that if you choose proper scaling here, then if you derive the dynamics for yt, some of the elements will cancel out. And this is what we see here. And they cancel out in a nice way that basically if we look at the dynamics for dyt, now after simplifications, after this term is out, this is gone, and if we collect all the dt terms and volatility terms, we end up with the dynamics for yt, which does not depend on a stochastic component. So there is no more rt, neither there is rt. So we have a lambda time-dependent function theta t, e to lambda t dt, and we have volatility from full white, so it's eta drt, and here we have e lambda t dwt. So you see there is no dependence on the rt, neither yt, and on the other hand we have the definition of yt is equal to e lambda t rt. This is just this definition. So from here what actually happens, so if we just divide both sides by e lambda t, then we have solution for our process rt, but of course we still have to integrate this part. But this integration, so if we would like to find a solution for yt, then we just integrate this process because there's no dependence on yt, so there's a direct integration, and then we find a solution for rt. And this is done in this term here. So if we have a dyt process, then we integrate from 0 to t, and then we have this solution. And then if we substitute that to this expression for relation between yt and rt, then we end up with the following solution for process for a whole white short rate model. So then we have a drift, no, actually not the drift, we have kind of initial part. So this is also the one that we discussed before. This R0 has to be implied from the yield curve. We have a scaling, which goes with the speed of mean reversion. We have a part which corresponds to the drift, so it's a time-dependent function here. And then we have also scaling, and then we have this volatility component, which involves exponent, and then we have also decay coefficient and interest rate part. In this process, actually, full white, you see that we didn't consider our volatility coefficient is eta, so this is slightly different what we have discussed in the HJM framework, but this is just a notation. It doesn't really matter. So eta is equal to sigma. This is what you have to have. And then what we have next, so once we have this expression, so we see that these two terms, those are just deterministic functions. So those would be, or from stochastic perspective, this is just a, you can say, constant time-dependent function. So there is no difficulty there. There is just integration, but that's rather easy because we can always integrate time-dependent functions. And then we have a stochastic integral from 0 to t, and then we have an exponent and then dwrz. So, but also here, because we are having this Brownian motion, this part is also deterministic. So this integral is normally distributed. There is nothing more than that. So RT is normally distributed and has an expectation and variance. Expectation obviously will be this part, because expectation of the Gaussian integral, it is just 0. And the variance will be driven, of course, we have to calculate ethos isometry to get the variance for it. But so the expectation here, and then for the variance, we use only this component by the Brownian motion. And this is what we have here. So the expectation of a process RT conditioned on today. So this is condition that we will see the process simulate for us from today. Then we have R0 exponent minus lambda t. And we have this other component involving the term structure, theta z. And for the variance, we have a composition of volatility squared divided by speed of mean reversion. Then we have also some decaying element here. If we choose long-term mean, so if we choose this theta z to be constant, then we can actually nicely see that we actually case of model of Vasicek. So this is the one that we have discussed once we talk about equilibrium models. So the ones that we will need to calibrate parameters to get our yield curve recovered from the market. So we have to always calibrate. Then we can actually see that expectation, long-term expectation, always converges to theta t function. In the previous course, in the course of computational finance, we have discussed the class of affine diffusion processes. In a nutshell, the class of affine diffusions is a class where volatility or the instantaneous covariance matrix and also a drift of a stochastic process are linear in state variables. The same would apply for Hull-White model or the interest rate models we discuss in this course. So if you look at this process for the Hull-White dynamics, we see that we have a time-dependent function. The dependent function, that's not really a problem for affine diffusion class. And then we have lambda times minus RT. So this is still linear function of our state variables because system of state variables is only RT. And then we have a constant coefficient sigma. So this basically means that the model of Hull-White belongs to the class of affine jump diffusion processes, and that therefore we are able to find the characteristic function for this process. This will be particularly important once we want to talk about zero coupon bonds, and we would like to find analytical expression for those zero coupon bonds we have seen before. So you maybe remember for Hull-White model or for those affine models, we can find a zero coupon bond, which is defined in the following way. To be an expectation, of course, we have into e to minus integral from t to t r s ds, and this will be given in terms of some function a plus b times rt. So in order to find those functions a and b, essentially we will be benefiting from the affinity of our short-range model. So now we will go through this derivations of the characteristic function, and from there we will calculate a and b's such that actually this will hold. By definition of the characteristic function, so we have characteristic function for process Hull-White, we have an expectation, and then we have a discounting, so it's a discounted characteristic function, and then we have IURT. Already at this point, we see that if we would choose u equal to 0, then we have here this term will be gone. Then we only have a discounting part, and that essentially would be equal to this expression which is here. So if I take u equal to 0, then we have equality between here and this term. So if we find the characteristic function for u equal to 0, essentially that will be this expression, because this RT is measurable, so we get it outside. So this is exactly what we want to find right now. So if we go through the derivations of the characteristic function, the characteristic function for the Hull-White process for u equal to 0 will be exactly the form we want to find the solution for this expectation, which is here. There are a few steps in derivations. There are also multiple ways how to do it. Here we will go via so-called decomposition of the Hull-White model. The idea here is to take a Hull-White model and remove the deterministic function, so this theta t function, and separate it from the mean reverting process, which does not depend on any time-dependent parameters. And this is how it's done. So we define process RT. We have a R tilde plus psi t, and then psi t is a function of time, and R tilde is defined as follows. So if you substitute those two elements, so if you substitute psi t and also R tilde, you substitute here, you derive the Ito integral, so you derive the Ito dynamics for this process RT, then you end up with a Hull-White model. The details on these derivations are in the book, but I would like to then skip it here because this is just an application of Ito's lemma. Okay, so this is the decomposition. And of course, now if we have this decomposition, we can also use this decomposition in this expression here. So this is what we will do next. So we start with the definition of the characteristic function. We substitute our RT. So now we have this RT is equal to R tilde t plus psi t. So wherever we have a RT, we'll substitute with this expression, and then we end up with a psi capital T. We have integral over psi, and then we have two functions, so two elements, which depend on R tilde. And this R tilde, it's without any more time-dependent theta t function. Those functions here, psi t and those integrals, they are not stochastic, right? Because we have just derived it here. This is purely function of time-dependent parameters. Yeah, so we have theta t function. We have also dependence here, time. This also is time. So it's basically psi t is just a time-dependent function. This means that we can take it outside of the expectation. So these two elements can be taken outside, and then we only end up with an expectation of Q of these two expressions, which is equivalent with the characteristic function for the R tilde process. So then we concentrate only of the finding of the characteristic function for R tilde. Because we know that the model is affine, then we also know the solution. And the solution is exactly what we have written here. Because model belongs to an affine form, we always know that there will be some A and B's that are solution of the Riccati type of equation. And there could be, of course, much more advanced processes. And we know that this is the form of the solution. And using the Duffy-Singleton theorem, we can actually find out those A and B's. So if we summarize what we see here, so we have done so far, so we have characteristic function for a full white model. We know that if we choose U equal to 0, then we know exactly this is a characteristic function at U equal to 0 is given exactly as the zero coupon bond. So this is zero coupon bond P, small t, capital time T. And we also know that because the model belongs to affine processes, then functions A and B are known or can be derived using Duffy-Singleton theorem. This, as we already have discussed in the previous block, this is very powerful machinery, because then in order to find the zero coupon bond, especially if we talk about the times Ti and Tj, which could be in the future, and this is essentially important once we talk about evaluations of, let's say, XVA type. So in an XVA world, we would simulate different market scenarios, and for different paths of interest rates, we will need to reevaluate our value of a portfolio. This means that we are not looking from perspective of today when we have a T0, but we are looking from perspective of future path realizations. This means that for every future date, we have to evaluate value of portfolio. And if portfolio is a swaps, for example, or other interest rate derivatives that we will discuss in the next lecture, then we need to perform multiple evaluations of nested Monte Carlo. And if this can be avoided and we can express this expectation, conditional expectation, if in terms of dependence only at the particular point RT of our paths, this will be significantly improving our simulation, and it's actually the essence of the core of the improvement for the simulation. So whenever we have a model for which we have to do nested Monte Carlo, that's typically considered to be very expensive and very often is rejected as the practice. However, models like Oosterlee or White, I think mainly White, are well adopted and accepted in the industry because of this excellent, powerful form. And also because we are talking about exogenous models, this also means that the calibration to yield curve is guaranteed. Otherwise, the model will need to be also still recalibrated to the market. So in the equilibrium models, the theta t function will need to be found with some optimization. That will be also considered to be extremely expensive, especially if we talk about 10,000 simulations, possible market scenarios for which we have to calculate value of our portfolio. And those functions a and b, they are closed form. We will derive it. I will show you explicitly what is the form for a and b. They are really one-liners, you can say. This means that you can just implement them in a single line. B will be a trivial. A will be a function of theta. As you can imagine, this function dependence on theta, so this time-dependent relation, it always included somewhere in those functions. So it's actually in A. In essence, in the formulation applies in the fact that there is no longer necessity of the performing the conditional integration. So this is the key element. Because we have this affinity, we have this dependence only on the paths at given time t, we don't need to perform nested Monte Carlo simulations to get the conditional expectations. So again, just to summarize, maybe I'm repeating myself, but I think this is really crucial. If we have some capital time Ti, we simulated our short rate models, then at this point, we can just substitute the value of a path to this expression, and then you see that if I would change our capital time T, it does not really change the path. So only I need to reevaluate functions A and B. So if I'm interested in a bond of this maturity or this time, or this time, and so on. I don't need to redo my Monte Carlo simulation. I'm only plugging in the same RT into the expression of zero coupon bond, and I'm just changing function A and B, which will depend on the maturity. And this is extremely powerful. This means that if I would like to price a swap with, let's say, 20, 30 years at this point, I don't need to do any nested Monte Carlo. I just evaluate this expression. So here we have a Ti, and here will be Tj, and this will be this tau here would be a difference between Tj minus T. And then we have a R, here we'll have also RT. So this is extremely powerful. As you can see, it's also a little bit puzzling how this happened, that we have now so much elegant expression that our zero coupon bonds depend only on this realization at this point. So for every path, I can just immediately evaluate the different zero coupon bonds without having this nested Monte Carlo. And that's extremely essential key in the HJM framework, in the arbitrage-free pricing of interest rates, and also in XVA. Without this relation, the evaluation of XVA, of simulations of portfolio for different paths, it would be extremely expensive. And I'm pretty sure that until now we would not really solve it, maybe against, except that if somebody would use it very, very heavy GPU computing to really get these simulations. Typically, if we take if we consider nested Monte Carlo, that's considered to be extremely expensive, and often it is rejected as the market standard. So this is actually here. So if we want to perform efficiently XVA simulation for many paths and large portfolios, this is the way to go. We really rely these days on efficient computation of zero coupon bonds, and if the zero coupon bonds can be expressed in this way, this is extremely beneficial. Those are the functions A and B. So as promised, I also provide here the closed form relation between a zero coupon bond definition and how those functions A and B look like. So you see, it's just a one-liner expression. We have also integral of theta. However, this formulation, which there are also alternative formulations which don't involve this integral of function theta. Here, however, I want to just make it explicit what is the how this formula looks like, and then B is also just a functional parameter. So we have, if we have theta function, we have a volatility, and we have a mean speed of mean reversion. We can just substitute those into A and B, and we evaluate at every path of RT to have every possible zero coupon bond. And let's take a look at the system code. So in the previous experiment, we were looking at zero coupon bonds which were used from the market. So this is our famous experiment. We repeated already a few times. So we choose zero coupon bond curve as 10% here, but we can actually change whatever we want. And then what we do, we would like to evaluate zero coupon bonds from the model. The first approach will be to calculate it using expectation of 1 over MT. So this is what we have done also previously for the full white model and also for the full E model. And in the second approach, I'm going to evaluate zero coupon bond using this analytical expression from the slide. So this zero coupon bond, you can see here, it involves two functions, BR and AR, and those functions are just defined as were shown on the slide. So if we look at A, we have time t1, t2. We define some grid. This grid is necessary for the integral. Then we have BR function is just the one that we have for B. And then we integrate, I just perform here trapezoidal integration over function theta multiplied with this BR. And then this means that for every t1 and t2, this expression is determined. Like I mentioned before, there are possibilities to avoid integration. However, to get to this, let's say, integration-free representation, it takes a few more steps. So if you are implementing full white model in production, then typically you will not go this way, but you will go a way which will avoid additional integrations. That's typically beneficial. Whenever you can avoid integrations, whenever you can avoid numerical computations, that's always preferred choice. especially if we talk about millions or hundreds of thousands evaluations for different Monte Carlo paths. And of course, if you talk about the large portfolio evaluation, this is also very important. So we have this A, we have B, and we just put to expression for zero coupon bond. So the zero coupon bond under the full white model is AR plus BR times, and then we have this RT1, which is an input here, and this input here, it is, you can see, it is only the R0. So we are looking from today's zero coupon bond curve. So we are looking at the zero coupon bond P, T0, TI, and then this TI, it is grids here in this maturity frame. So if you run the simulation, you see it's everything is nicely spot on. And again, as we have seen before, now we can actually, we don't need to do this nested Monte Carlo. We don't need to look at the money savings account. We can directly calculate zero coupon bonds using essentially just the evaluations of function A and B in this case. We don't even need to simulate the whole white model. As you can see, this whole white model is evaluated at R0 because we are looking from today's perspective. So this expression here does not even involve Monte Carlo simulation. So zero coupon bond for the whole white. If we look from today's zero coupon bond curves, we don't even need Monte Carlo simulation. We have zero coupon bonds explicitly in terms of function A and B and R0. So this is why also this is very important to have this R0 defined as the, let's say, the shortest instantaneous forward rate. So this, as you can see, it's very powerful. Even we went further, we don't even need Monte Carlo simulation. And it's also very fast. And now also we have this extra 2 degrees of freedom, mean reversion and volatility that we can use to calibrate to some derivative of interest. So for example, if you like to price Bermudian swaption, then would use those parameters to calibrate the Bermudian swaption or the volatility surface. Then we have those 2 degrees of freedom can be used in that respect. So if we look, so this is me, let's take a look here. So in the case where we have t equal to t0, then we have r0 here. So then you see there's no stochasticity anymore. So if we just choose r0, we calculate from the instantaneous forward rate 0 epsilon, and we substitute here, we can calculate directly all the zero coupon bonds we want without even simulating of interest rate. And before, how we were doing, we were calculating this zero coupon bond, so expectation of E minus integral from t to capital TR S ds, given filtration T0. And then we had also, this is equivalent of expectations of 1 over M. This will be capital time T. And here we have M small time T. So if small time t is today, this quantity is 1, so this mt is 1, and here we have m capital time t, and this is equivalent with the e to integral of from t to capital time t rs ds. So this is equivalent. Now, even if we have whole white closed form representation, we even don't need to do this simulation, which we have done before. Yield curve is one of the most important elements needed to determine present value of future cash flows. Construction of the yield curve is a job for a financial engineer. And so this is very important that you know the principles, how to build the curve, what is the meaning of the curve, especially since the usage of the curve is essentially day-to-day operation in any financial institution which has to deal with interest rates. However, even yield curve is not only used in the world of interest rates, it's used all over the place in every asset classes, even stocks, FX, etc. It's always, we are talking about the yield curve, and the yield curve is one of the most important elements in each of these classes. In this course, we will discuss how to construct a yield curve, how to map, how to find a curve given number of market instruments. This will be discussed in the follow-up lectures. However, now I would like to give you only the flavor what is yield curve about, especially since I would like to use this information, this knowledge, to give you some more insight regarding the short rate models that we have discussed. And also, we have seen that, for example, the full white model we have just covered, it is You could also say it's a Ferrari among all the models. However, there are also limitations. So this one-dimensional whole-white model, it is not always the most desired model if we talk about risk management. So later in this lecture today, we will discuss advantages and disadvantages of using whole-white model, and also the extensions of whole-white model from single factor to two-factor model. And I will show you exactly how to perform the experiment where we can see the impact of adding second factor to the model. However, now we have to understand, we have to build this knowledge, we have to get more information regarding the yield curve. Yield curve, so like I just said, is one of the most important elements when we talk about present value of future cash flows. Yield curve is used to discount all the future cash flows. If we talk about the instrument that has future cash flows, then we always discount using yield curve to today. So essentially, if we have cash flows, it's a very simple graph. So we receive this is at time t1 certain amount C1, at time t2 we have amount C2, and T3 we have C3, and so on. These are the future cash flows. So of course, today, if we are here at time T0, those values, we need to bring them to today. So 100 euros, let's say, in 1 year is not the same as 100 euros in 2 years, because there is a time value. So if you like to calculate the present value of this cash flows, so let's say constant cash flows, then we will be talking about the discounting of those cash flows. This will be to Ti of those cash flows Ci. So this is our present value PV. So you see those elements here, those discount factors, they are not taken randomly. They are not chosen just directly taken from the market. Typically, if we have market instruments for interest rates, first we would bootstrap, calibrate a yield curve, and then those discount factors will be used from that curve. Okay, for a given yield curve, one is able to provide forward rates. So like we see here, using different maturities of the zero coupon bonds, we can construct forward rates. That will be discussed in the next lecture once we talk about LIBOR rates, and we will dive into particular instruments in the interest rate world. And also the very important instrument that we'll be covering is, for example, interest rate swap, which is one of the most important instruments in the interest rate market. The main concept of a yield curve is to map market quotes of liquid instruments to some one unified curve which will represent the expectation of the future rates. So those zero coupon bonds, if we think of, let's say, I'm always plotting those Monte Carlo paths. Of course, the future is not known, right? So we have different type of scenarios. However, if you look at those discount factors, those are just known today. So you can say that actually there is a market expectation. Maybe it's not the best color here. Do this. Market, those zero coupon bonds, they are representing the expectation of the market of all the possible scenarios. So you can imagine you can have a million different or infinitely many possibilities how this future, where the rates will be in tomorrow and the after and so on. But once we talk about interest rate product, essentially every interest rate product is an expectation of the future value. So if we talk about the yield curve, we built a curve constructed out of the expectations of future instruments. So we see market gives you expectation of the products, and we use those expectations to build a yield curve. So this is important. So we see that every day the curve will be different. However, we look at the expectation. What is the market expectation? So the current value just shows you what is the PV, what is the current value of the instrument. And of course, if we move to tomorrow, then the value can change, and that will be also expressing a difference of your PV. In a few slides, we will perform some simulations regarding different scenarios, how to simulate a yield curve, and how to really understand how those Monte Carlo paths, which I was trying to plot here, and also this yellow line, which represents the expectation, how to put hands on, how to simulate that, and how to get this yield curve out of those Monte Carlo paths. A yield curve is constructed from discrete set of instruments. So we already have discussed it, that we have those different periods. So typically we will have, let's say, T1 here, T2, T3, and we will have those zero coupon bonds from the market. And then we would just impose some kind of, actually this is depending on the yield curve shape, we would impose some interpolation, and from that we will get our yield curve. Why we have infinitely many instruments we don't use for the curve construction? It's typically because the instruments which are chosen to construct are typically the most liquid instruments. So if you imagine a situation where we price an exotic derivative and we use the yield curve, and yield curve, the price of exotic derivative, if we would calculate Greeks, we would also show the risks with respect to instruments built on a curve, because typically those instruments could be used to hedge the exotic derivative. So what that means that yield curve should be always built for the most liquid instruments, because we will use those instruments as the hedging instruments of some potentially exotic or less liquid product that we want to price. So it's important to think that yield curve is always, we always choose those instruments according to liquidity, and not really price, but always the liquidity. So that's the key point here. Then the effect of the interpolation. Imagine if those points, this is not really liquid, there is a huge bid-ask spread, so this instrument could be here, then you see that could be huge impact on the overall discount curve that we would use in calculations of those PVs. So remember, always the most liquid instruments, and as many as possible, basically. That's typically the case. However, number of instruments that you would use in the construction of the yield curve may change in time. And then we will also have to deal with a problem of how to compare different yield curves from one day to another one. That will be discussed in this course at the end, once we talk about historical VAR calculations. The yield curve is often viewed as a leading indicator, providing an early warning on a likely direction of the country's economy. And this is a nice example. Yield curve has historically become inverted 12 to 18 months before the recession. So in a few slides, we will discuss particular shapes of a yield curve, and then how to associate those different shapes to overall state of economy. Important also element once we talk about the yield curve is that central banks are often very much present in the bond market. So this means that the yield curve could be also significantly affected by the monetary policy of central banks. Maybe one more thing, once we talk about yield, so this is also important. You see here I plotted zero coupon bonds, but typically once we talk about yield curve, we have to map those zero coupon bonds to yield. So how this takes place, I will give you details on next slide, but remember in a definition of a zero coupon bond, we have a P0T, then we have expectation, we have this exponent with minus integral from T0 to T RS ds. So this is given those Monte Carlo simulated paths, we can calculate this expectation. However, of course, we see that there is many different scenarios that could be used to calculate this expectation. So once we talk about yield, we always impose a certain form here. Then we have minus R, and then we have a T minus T0. And this R here, it is typically called yield. And yield is always in units of years. So if you have a 5-year yield, this means that you will get your payment over a yearly basis. This R here, it is also often called effective rate, because you see all this integral information about the short rate which is used in this integral, we compress that into one particular number. So effectively, we mapped the yield, the whole scenarios into one number. So you can also think like this. We have T1 here, we have a yield from today until this moment. If there will be a T2, for example, then we have yield over this period. So you see that there is an overlap of all those yield instruments which are used here. So if you like to have so basically longer the bonds that we use, more information has. So always the next bond, let's say bond with the next maturity, will always contain information about the bond from the previous maturity and additional element. So if you like to have time-dependent R, in this case, you need to make sure you have to bootstrap this R to be time-dependent such that those, let's say, effective ones, so the integrated ones, will match still the instruments in the market. But that will be clear, I'm pretty sure, in few slides we'll go over again, and I will provide you more details on that. Yield curve reflects not only interest rate expectation, but investors' attitude towards risk and their need to different maturities of the bond. So of course, if we have a situation when there is a crisis, typically people try to sell their assets, their stocks, and they keep cash or buy short-term bonds, because from bonds you typically get, at least maybe not in Europe, but in other countries, you may receive a rate, overnight rate, which could be non-zero. So that's always better than keeping your cash. And then of course, if the demand for short-term bonds is higher, this means that the yield goes lower. So this is also, you can see, yield curve also changes. With different shapes of the yield curve we will discuss in next slide. A little bit maybe mathematics on how this mapping of zero coupon bonds, how this process of mapping zero coupon bonds to yield curve and how this yield curve will be constructed. This is the slide where I give you a little bit more details. So a yield curve can be represented as a set of nodes. So we have a set, you see, for every time we have a df T1 to df T2 and so on. So this is typically associated, those pairs are associated with our nodes on the yield curve. So those are like often we call it spine points on a curve. And then by definition, as I have written in the previous slide, dfti is equal to zero coupon bond. This is important. This is actually today. So from today to particular moment. And then we have discounting from time t0, from ti to time t0. So we have this integral, and we encapsulate that with by stressing that we impose that this, let's say, stochastic expectation is represented as the simply compounded rate. So it's a simply compounded rate. In the course of computational finance, we discussed about the discrete compounding and continuously compounding, and I also gave you the proof how to switch from one to another one as the, let's say, time step decreases. So we compress, because of course we also don't know what those paths will be, but we can always say, we can always impose the condition that this should be equal to minus r. Of course, this will be ri, and then we have a ti minus t0. This is what we can impose on this bond. And then r will correspond to the yield of this particular bond. Okay, mathematically, a yield curve is a function which maps a discrete set of zero rates into real numbers. So we have those pairs, we have a T1, df1, and so on, and we map it to the real numbers. Of course, here it is also a real, it could be positive. Actually, in this case, the zero coupon bonds are always non-negative, but could be, for example, that they're bigger than 1. So this means that your rate that you have here, it is negative. Then you have a value which is bigger than 1. And typically, the set of points, so those points we have discussed here, those are called the spine points of a yield curve. In essence, the spine points are directly implied from calibration instruments. So the details how to calibrate those spine points from the yield curve, I will present you in, I think it will be in 2 lectures. There we really go into details on how to find optimal spine points such that we can actually price back our instruments that we have used to construction of the curve. So if you think of a spine point, this is similar as our spines in human beings' spines. So each of those bonds, spine points are used here. And then in between, we have to choose some kind of interpolation routine. So again, if we talk about a yield, or we have a zero coupon bonds, so it's here, those are let's say here. And then we take interpolation between all those points. This is how we get bonds in between. So if we have here, this will be, in this one will be P T0 T0. Of course, by definition, it should be 1. So if you have so this is time here, and here is a value of a zero coupon bond. If we have here time T1, here's T2, T3, T4. Then we have those spine points. We define interpolation in between. And typically what is very interesting is that interpolation can vary whether we are in a far end from the curve or the initial part, so in the front or the back end of the curve. And then these interpolations actually can change. This depending on the choices, often from what is the market convention, what is also possible as the trader's choice. Why we need these interpolations? It's basically, like I just discussed, we have spine points, which are determined based on the most liquid market instruments. However, we don't know the points in between. This could be, for example, liquid instruments. However, once we have spine points and we have defined interpolation between, we can imply, for example, for this point, we can calculate zero coupon bond T0, let's say T1, oh, let's make it here T0. This will be T0. So you see, we can, because of the interpolation, we can calculate this bond. And if there is a client who like to buy this bond, then given this interpolation, we can sell him. We know the fair value of this bond, given, of course, the model assumptions regarding the interpolation, we can sell this bond to the client. And of course, somebody could say, yeah, we have multiple choices regarding this different interpolations. This is why this interpolation is so much important, to make sure that even if you have maybe some illiquid instruments, that your interpolation choice is not really far off even from the illiquid instruments. So as much information you take into account in building of your yield curve, it is your benefit, and always at the end it pays off. What is also important is that here, if we have an instrument which would depend on this point, and we talk about sensitivities, the hedging, which we'll be also discussing in this course, then the sensitivity could depend either on the neighboring points. So, for example, it will be dependent on these 2 points, but also could depend on those points. So if you have a bond, in this case, sensitivity hedging of this bond would require that we need to buy, for example, 4 bonds on the sides. If you have different interpolation routine, for example, linear, that would only require neighboring zero coupon bonds. Of course, if you think about it, that you have a bond with this particular maturity, let's say here it is, let's make it T star, and somebody tells you that you bought a bond or sold a bond with a T star, and in order to hedge that risk, you need to buy bond with T4 or T1. This sounds a little bit strange, because this means that you have one instrument here, but your sensitivities are really far off the curve. So of course, the choice of an interpolation would really play a very significant role, how your sensitivities, how your risks are affected by different interpolation. In the 2 lectures from now, we will go through details how to build this curve. Exactly, we'll see this impact of a construction of the curve, and also the hedging, how these different interpolations would affect your hedging performance. And you will see actually nicely that if you have an instrument here and then you choose interpolation routine, it may be that you have to buy instrument, if this is, for example, 20 years, you have to buy 70 years instrument to hedge that risk, which sounds very unrealistic. So, for example, you have a loan of 1 year, but in order to hedge that loan, you have to sell a loan with maturity of 50 years, which is, you could also consider to be a bit silly. So, and that has to do with the interpolation. So, those things we will discuss later in this course. Let us now summarize what we have learned so far about yield curves and what are the conventions regarding the naming of a yield curve and how this is related to zero coupon bonds. From the course of computational finance, we already have discussed the definition of the continuously compounded rate and how this is related to discretely compounded rate. So continuously compounded rate essentially is equivalent to this expression E minus RT. And then, since we have talked about zero coupon bonds, we say for constant interest rates, this is the form for the zero coupon bonds. And of course, from the theoretical perspective, the zero coupon bond will be associated with expectation of exponent of the integral of the minus integral of short rates. From here, we can also compute R, and this R is actually called our yield. So zero coupon bond is it's a zero coupon bond. It's a tradable asset. R is a yield that we would receive if we would invest some amount of money in this bond, and we will receive €1 at the maturity. So once we talk about yield curve is associated with pairs of points. We already have seen those TIs and DFTIs. However, once we talk about the particular yield, then we can easily switch from zero coupon bonds to this R. So then typically we have R is a convention. So if somebody says we have a 5-year 5% yield, then you know how this is related to the zero coupon bond, how this is related to spine points on the yield curve. That's the convention. I think something I already have mentioned before, if we have a zero coupon bond, PT0T, and we have a expectation, we have a minus, and we have integral from T0 to TRS ds. If you take just an expectation of the integral here, that's not equivalent with expectation of the whole term. So if we talk about the yield, we always have to go through this expression here. We cannot just take expectation of the exponent. I have seen this mistake multiple times, so please be alerted. If somebody considers full white model and talks about yield, never dare to take the expectation from the integral under this expectation. So because this is expectation of e to power integral is not the same as exponent of an expectation. So then please be careful. If we talk about yield, it's always associated with this term. This is just integral of the short rate. So this is something different. If we talk about the full white model, we already know that under, this is a small typo here, this should be not the zero. So you see that's this is also here the same. This always has to be consistent. So if I'm looking at the equation and I see there is inconsistency between filtration and some integrals, that's always an alarming signal, because this means something is wrong in the equation. So here now everything is fine. So we have zero coupon bonds, again the expectation, and because we are dealing with an affine full white model, this zero coupon bond can be expressed in this way. And then we impose this continuously compounded rate, which is this effective rate R. So you see this A and B will be kind of compressed into this R. So this R here is different than R here. So keep that in mind. Maybe it should be actually here we should talk about tilde. So this is one which is from the full white model or time T0. This is yield, which represents the whole zero coupon bond. And from here, what we can also do, we can compute this yield. So under the full white model, yield is equal to minus, and then we have, of course, if we just take a logarithm of A and B's with a minus sign, we have 1 over T minus T, AB, and then we have this RT. So this is our yield. What we will do in this lecture today, we are going to simulate full white model, but we are not going to look only at the yield from today, but we are going to discuss how the yield curve dynamics of the yield curve constructed from R's, how it behaves in time. What is the dynamics of a yield curve on each stochastic path? And that we will compare to, let's say, more realistic case that I have prepared also for you. So those will be very entertaining to see how we can see on historically the dynamics of the yield curve and how this can be related to the full white model, how we can simulate that yield curve and how to really compare the shapes of different yield curves, and then moreover, what is the impact of adding second factor to the dynamics of this process. So comparison between one factor model and two factor models. Yield curve, so if we plot this R, so not zero coupon bonds, but R, then we have a multiple different shapes. Right now, I would like to, because it's only a brief introduction to yield curves, I would like to just give you a little bit of flavor what are possible shapes. We will discuss it in more detail in the lecture dedicated to yield curves and yield curve construction. So this is a so-called normal yield curve. So we have a short term to maturity yield is lower. If we talk about the long end, then it's much higher. Why it's considered normal, this indicates a healthy economy, because, for example, if you look at the banking perspective, a bank, if you have a mortgage, for example, bank would lend you at this rate, let's say here, and financing of the bank will be at the short term. So you see, banking industry, which is an engine of the whole economy, would make roughly this spread. So banks typically, if they issue a mortgage, they finance the mortgage on a short-term paper, so they borrow money on the short term. However, they lend you at the higher rate. So this is a healthy environment for the economy. This is why often once you hear maybe about the quantitative easing, then central banks typically start being active on the short term of the curve. So this means that they are trying to decrease the rate by buying bonds. They decrease the rate to push it as low as possible so that this, let's say, healthy economy is imposed by the central banks. This doesn't always work because, for example, if the central banks pushes this point lower, but markets still can move this point lower too. So then you don't really see the benefits of quantitative easing. But of course, central banks can try to manipulate or try to influence different shapes of different yield curves by the quantitative easing, by their presence in the bond market. This is a case of a flat curve. So as you can see, compared to the previous case, long-term yield is almost the same as the short-term yield. This is a sign, typically, this is a transition between a normal yield curve to so-called inverted yield curve, where the long-term yields are lower than the short-term yields. That's typically associated with a crisis or market perception of an oncoming crisis in the market, in the financial world. And this is typically flat. It's a transition between a normal curve and an inverted curve. And of course, in banking, we already have discussed. So if bank lends you at this rate, but finances at almost the same rate, the difference is much smaller between the two. And that also means that banking is much more, there is no so much interest from banks or other financial institutions to lend money for long periods of time because there is not so much benefits for the bank. So this is also means there is a kind of feedback loop because if banks they don't issue more loans, then this will also not have stimulating effect on the economy. And this is I have prepared also a graph from Treasury, from the US Treasury, where we see the dynamics of the curve. So how the yield curves behave in time. So this is 2018. You see there is you could say, normal yield curve. So for a 1 month rate, it's around 1.9% or almost 2%. 30-year yield is 3%. And then in 2019, so we have a July and August. You see the July is already inverted. So almost inverted. So there is some kind of here a bump, and here in already 1 month later, the long yields from the long term they moved even further low, and that's typically a sign that something market expects something very bad in the economy. And actually, what you can see, this is also maybe some of you remember, in October in 2019 there was a so-called repo crisis. So this you can also associate with this yield curve behavior that is a signal of something bad coming. Central banks typically are active in a short end. They could be also active with a long end, but that's in a case of so-called yield control. So if the central bank sees that controlling short term does not really have a good impact on the rest of the curve because market is in turmoil, there is yields going up. For example, if there is inflation expectation, this means if the rates are going extremely high, then central banks may also decide to control the whole curve. That's called yield control. And that's also not a good sign about overall economy. You can also see 2019 yield curve was inverted. I'm not sure whether there was also market had this insight about the Corona crisis. However, it had a good feeling about the forecasting about the repo crisis, which was in October of 2019. There's also something which is often seen in risk management once we talk about parallel shift of a yield curve. So if you have a book consisting of multiple assets in your book, then you want to maybe see what is the impact of the yield curve shape. So shape is the same, but we bump our curve up and down, and so we can compare the impact. We can see the impact on positions that somebody has in the interest rate world. And this is so-called, if it goes up, we call it upward shift, parallel shift, and then if it goes down, it's a downward shift. Of course, if you buy a bond and you have guaranteed payoff at the maturity, it doesn't really matter how the yield curve will behave because you know that you have paid a certain amount of money and you will receive principal, which is guaranteed at the maturity. Of course, it's nicer if you buy something cheaper and you receive principal of, let's say, of €1 in the future. So if in the case of zero coupon bond, it's always nicer if you buy zero coupon bond for 50 cents and you receive €1 in the future, instead of buying at 99 cents and receiving €1 in the future. That could be potentially considered to be potential loss. If you buy a bond, long-term bond, and you keep it, then this changes in yield curves, they don't really matter so much. Of course, there could be extra effect, which is related to inflation. And because inflation, if there's a high inflation, your €1 that you will receive in the future, it will be worth less. And that's also something which will have also impact on interest rates. Market will try to price in inflation in the yields. And inflation topic we will also discuss at the end of this course. So this will be also a nice composition of discussions about interest rates and also the impact of inflation. I have prepared a kind of interesting video. So this is the material which I have found online. It is basically a video which shows us the dynamics. So let's try to explain here. The most important curve here is a curve which is the blue curve. So we have blue, which is effective Fed fund. So let me move my. Let's show what you can see. This is the legend here. Okay. So you have a blue line is the effective Fed fund rate. This you can consider as a short rate because this is over one night rate. We have a SPX, which is the index American S&P 500. And then we have a red, it's not maybe so much important, is the relation between 1 and 5 year and 1 and 10 year and so on. So let's focus here on two things. So the blue line, which is a short rate, you can see overnight rate from Fed. And we have a blue line, which is essentially is a yield curve. So remember we discussed construction of a yield curve where we have a R0, and we can, from this R0, we can build zero coupon bonds for all the maturities. And this blue line, it corresponds to that. So we have here we have let me see, let me show you. So we have a blue line which is in this point here, and we have a green line which is moving in time. So you can see so this R0 is moving up and down, and the green line is this corresponds to the yield implied from the market. So this is the market expectation. So this is 1986. So you see this, now it's a flattening of the curve, and there was a crisis, and then you see it's market recovers well. So if you look at this S&P, so there was this, you see it's a spike down on the orange line, went very much down, and that also had impact on the curve. Now we see an inversion of the curve. So this is beginning of 90s. Now the curve is flattening. That's not good for the banking. So let me scroll a bit maybe further. An interesting period is of course 2008. This is 2008, let's see. This is 2006. See? Yes, so we have, this is 2000, now it will be .com bubble. So flattening of the curve again. And then 2000. And S&P, let's see how this will move down. Oh, now it's going down, and the curve is inverting again. Oh, this will be a significant shock. So the rates immediately, people move to the treasury. So you see the curve parallel move down. So this means that money from the stock market moved to the treasury. So they moved to the bonds because that's considered to be safe haven. Then there is now the market recovers. Let's take a look. This is 2006. Now this is recovery after already financial crisis. So this is after 2008. And now you see flattening of the curve. Not too good. Oh, sorry, this is 2006. Oh, this is 2006. I was looking at the wrong here. This will be now the mortgage crisis. 2008. Yes. It's a dramatic move on the curve. Of course, the yields immediately go down because everyone investing money into the safe haven, which is considered a treasury bonds. And then you can see the yields immediately go down. Of course, the federal bank also cuts rates to stimulate economy. So this is a very nice link, and I will put the link in the description so you can watch it yourself, and hopefully you can also learn on the dynamics of the curve. What we will do next is to, so we see this blue line, we will simulate this blue line using whole-white model, and for every scenario, so for a given path, we will generate yield curve using the formulas we have seen. So it will be this exponential form. So we have this zero coupon bond, T, a capital T. We will have E, we have A, T, T, plus B, T, T times R, T. So what we will do, we will simulate the short rate, and every time on the path of a short rate, we will construct the zero coupon bond. So it will be first bond, second one, and so on. And then we will observe different dynamics of the yield curve. In this very interesting experiment, we have seen the relation between the short rate or an overnight rate and the dynamics of the yield curve. So this is basically finishes our first block of this lecture. In the next block, we will discuss further the short rate models, but we will do also something special. In the video we have seen this relation between curves and short rates. We will try to replicate that behavior using short rate models. So we will simulate a short rate model, and for every single path, every realization from the short rate model, we will generate a yield curve. And then we'll observe how this yield curve behaves with respect to different realizations, different Monte Carlo paths. And given this dynamics of the yield curve or the short rate, we can conclude whether the model is realistic, whether the shapes of a yield curve are realistic, especially from the market analysis, so the risk management perspective. So in next block, we will concentrate on more realistic dynamics of a yield curve implied from the short rate. So that will be 3 blocks in 3 different subjects covered in the next block.